Hello everyone, this is Kasi Lakshmanan again. This is a continuation from the short demo that you saw in the previous video. This is part of the E89 deep learning class. The topic for discussion is case study in finance. We will talk about risk scorecards and deep learning as a use case for risk scorecards. Risk scorecards are essentially classification models which predict the likelihood of inability to pay. Credit risk models have high target class imbalance, and we look at some strategies for that. We will also explore KerasTuner for fine-tuning neural network hyperparameters. The datasets we will use today for this exploration is the home credit default risk dataset from Kaggle. After some initial data preparation and some exploratory data analysis seen here, we will start off with some of the data treatment options. We will first look at the imbalance of the target class. So we have about 8% total positive class, which is a very highly imbalanced data set. We will also next look at the imputation of missing values. We assume that the missing data is missing at random, and we will use mean missing imputation. It's also important to note that missing value treatment is very important for deep learning models when in comparison to the gradient boosted trees, where the technique itself will account for the missing values in the model fitting. We'll do some usual steps: test train, validation, split, and then we will do some feature scaling where we will consider standard scaler. In all of the deep learning techniques, it's important to scale the numeric values so that the gradients are able to handle some reasonable values. So we'll go ahead and do that, and then we are ready to train our first set of baseline models. In the first baseline model, we will use a Keras sequential model. We'll define some of the metrics because we want to be able to also track some of our specific metrics that we want to track, like AUC, area under the curve, precision recall curve, etc., as shown here. So we will be first define them. We will also define a function that takes those metrics, and then it's a sequential model with one layer of 16 neurons, a dropout layer, 50% dropout, and then we will close with a dense layer that will have a sigmoid activation. In the compilation phase, we will use Adam optimizer. As shown here, we'll start to build a baseline model here. We will use early stopping with patients 10 on the validation AUC to do an early stopping, and then we'll go ahead and build a model and evaluate this model on the test population. We've defined some functions here that we can use repetitively through the process to evaluate, and we have a test AUC of a 0.727 as shown here. This will be a baseline model that has no tuning. Now let's talk a little bit about fine-tuning these network hyperparameters with KerasTuner. In deep learning literature, often authors cite network choices like 2 hidden layers, 20 neurons. They also cite Adam optimizer as the most optimal optimizer for a certain problem in hand. But these are usually set based on data set in hand and some careful tuning of the hyperparameters. This process is also very time and resource intensive. We will look at KerasTuner for this, which is a general purpose tuner which is available with the Keras modules. So first we'll install them, and then we'll start off by first defining a function which will, as previously seen, define those metrics, and then it defines some of the hyperparameters for hidden layers and for neurons, and then the learning rate and the optimizer choices. Then we will go ahead and define the model with a loop that goes into for the selection of the layers, number of layers and number of neurons in each layer, and also add a dropout and a dense layer as we've seen before. As a stretch, we could also even use a dense for the dropout criteria. We could use that as a hyperparameter as well. That could be a stretch exercise. Now we'll go ahead and compile the model, and then this would be the function we would use to evaluate around different tuning strategies. So let's look at three tuning strategies for this particular data set. We will use our first use a random search tuner. In the random search tuner, we will be able to first define the search tuner um, with a random search. We will use the function that we defined before, and then the objective, which would be the AUC object, and then we will run it for about 50 trials. And then we'll run the search tuner, and this takes about 3 hours to run. And then we will look at the top 3 models here. The top model in this, the best model, had one hidden layer with 36 neurons, and then it retained the dropout layers and the dense layer. We'll save the model, and then we would then evaluate this model on the test data set. So as you can see, the random search tuner did pretty well when we compared with the baseline model. Next, we'll move on to the hyperband tuner. The hyperband tuner is slightly a variation of the random search tuner, where it searches for a few epochs and keeps the best epoch in each search. It uses a strategy similar to the halving random search CV strategy in the sklearn package. This strategy basically generates many hyperparameter combinations and uses a random search to come up with candidate models, and then does a limited resource training where it uses smaller data sets than the full data set or other options that we can choose, and then cross validates the model. The best model in each round then moves on to the next round, and then so on, and then the final candidates are evaluated on the full resource, meaning the full data set. Here we will, in order to be able to run the hyperband tuner, first we will need to subclass the hypermodel class, and then we have two functions there, a build function that will use the make model function that we considered before, and then there will be a fit function, which will a fit method, which will basically take the train function and then the training labels and be able to fit the model. We'll do the similar. Before we move on to try to define the hyperband tuner, we want to look at how we can determine the number of trials it runs. The number of trials it runs is based on the max epochs and the factor. This is the formulation for that, and then we've run some scenarios here to look at how many trials it runs approximately. So we will choose a max epoch of 20 and a factor of 3, which will come up to about 148 trials. And then we will define the hyperband tuner with that criteria, and then we'll run a search on it with the early stopping callback as well. So it took about 44 minutes to run with 30 trials completed. So we will also do a similar exercise where we can look at the best model and then run an evaluation on the test data set. We can see that the hyperband tuner does slightly better than the random search tuner on this baseline model. Even though the hyperband tuner um, is slightly smarter than a pure random search in the way it allocates some of the search resources, in the sense that it runs on a smaller data set, and then once it comes up with a hyperparameter space, it runs on the full data set, but it's still very coarse, even though it's very fast. So we will look at the Bayesian optimization tuner, which gradually learns by fitting probabilistic model called a Gaussian process, and then zooms progressively in on the best hyperparameters. The downside to this is that it will has its own hyperparameters like alpha, which represents the level of noise you expect in the performance metrics, and then the beta, which basically specifies how much of the algorithm you want to explore instead of the good regions of the hyperparameter space. So that is the Bayesian optimization tuner. So now we will use the same my classification hypermodel that we defined in the previous section, and then we will run a search on for about 100 trials in this case. The best model from a valuation AUC had a 0.739. We will run our evaluation on the test data set. The evaluation comes up with a 0.730. So when we compare the three search strategies, I think the random search strategy and then the hyperband search strategy did a very good job with the test AUC. The Bayesian optimization tuner did a very good job with the validation AUC, but then it didn't generalize as well. Now, to close out this KerasTuner topic, there's one more tuner that you can use, which is the sklearn tuner. Even though KerasTuner is named that way, it's a general purpose tuner, so you could potentially use this on a sklearn model. So here there is an example on how you would you use that. Another related topic is tf.distributed. Hyperparameter tuning is very time intensive. Some of the scenarios that you could run would potentially take like 6 to 9 hours, even with collab with GPU resources. One way to reduce the time in processing is to be able to distribute the processes to run in parallel. Hyperparameter tuning is very well fits that use case very well. In this case, we will use a tf.distributed, which you can use on any fit method in Keras. First, what we need to do is we need to define the resolver, and here I used Colab. So I defined the resolver and then defined the search strategy. You could just potentially define a model, which I have done here, and then within the strategy scope, you could define the metrics and define the model and then compile the model. And then the next step would be to be able to fit the model. Potentially, you should be able to get a faster response time. The last one I have here is a stretch exercise. Typically, you would want to combine your tuning strategy with a distributed computing strategy, where you should be able to run the candidate models in a distributed mode. So in order to be able to do this, what you need to do is define the distribution strategy as we seen before, and then use that distribution strategy in your tuner search. So this is a stretch exercise that you could do. There is a link here for more information on this. Now let's move on to two other strategies that we can try to further optimize this model. One is refitting the model with class weights. We've done that for the three tuning models, and then we will also fit a challenger model with minority oversampling approach. Once we've done that, we can finally do some model comparisons. As you can see here, first things first, the baseline model with no tuning in all three cases did a very poor job when compared to models that were tuned. Secondly, parameter tuning also reiterates some of the conventional wisdom that we have. One is that in this case, the Atom optimizer does a very good job across all of the scenarios when we compare the stochastic gradient descent. Secondly, models with the smaller number of layers and many neurons do a pretty good job with respect to test accuracy or test AUC in this case, when we compare models with many layers and many neurons. The other observation is that the Bayesian optimization tuner, even though did well in our case with respect to um, the the Bayesian optimization tuner tuning on the baseline model did very well with respect to valuation AUC. From a generalization perspective, across all of the scenarios, it didn't do that well. On the contrary, for all three scenarios, the baseline strategy, the champion strategy, and the challenger strategy, the hyperband tuner and the random search tuner did a very good job in terms of the test AUC. So overall, we can conclude that the baseline model hyperband tuner and the class weights model with a random search tuner kind of tied with test AUC, and we could classify them as one of the best models. And then we can also conclude that they generalize very well with a slight increase in the test AUC for both scenarios. So let's conclude with a quick recall on some of the stuff that we talked about. So we talked about fine-tuning the models with different tuner strategies: random search, hyperband, Bayesian, and then the sklearn tuner and the tf.distributed. We also talked about the two strategies that we used for imbalance data: class weights, and then oversampling the minority class. Hopefully you enjoyed this presentation. Um, Thank you.